This is the barrel section of the injection unit on my machine, and in here we've got 4 heater bands and 2 more at the tip, which are basically to give you a little bit of fine control over the plastic you're injecting. And the lid's off this because I've had to hotwire in some thermocouples in the past. The main connecting block is actually buried right down underneath the cylinder, and you can't access it without separating the drive unit from the cylinder unit, and I've been advised not to try that because it might not go back together again afterwards. Now, this heater has been dicky for some time, but it's only on the feed section, so I've been able to limp along without that. It's not too critical, but now this one's gone down as well, and that's a bit more of an issue because it means I'm basically relying on these 2 at the front to do all of the heating of the plastic, and that's not great. So I'm going to see if I can figure out what's wrong with this. It may need replacing, which could be a struggle, but we'll have a look at the control side first, because I suspect the issue is actually in the electronics, not the heater itself. This is what's happening when I switch the thing on. It starts to power up the solid state relay and the temperature does creep up, but then it faults out, and if you do that a few times you'll see the temperature keeps rising, and in the background I can hear pinging coming from the heater band, which indicates that that is indeed working. And I get the same thing happening on zone 1 as well, which is also allegedly dodgy, but as you can see that temperature is slowly drifting up, and the more I do this the hotter it gets. So there's nothing actually wrong with the heater band, and the solid state relay that powers it must also be working. Therefore I think the problem is on the control side. So I'm going to have a look at that and see if I can figure out what the problem is, and more importantly how to fix it. When I bought this machine a long while ago, I was lucky enough to get the service manuals with it, and so I've got a schematic of the main heater board in the control cabinet, plus some rather limited explanation of what's going on. But I've also got the circuit diagrams, and these are actually the same diagram, showing the basic configuration for the control circuit on this. You've got a main input down here which is driving the solid state relay on the duty cycle. They're then using an inductive connector here, basically coupled inductors, or sort of transformer if you like, which is then controlling a couple of transistors and a couple of Schmitt triggers here to tidy up the signal, which is then firing through an opto-isolator and sending a signal back to the main processor unit. So I suspect that there's probably something wrong in this circuit, and it's not an enormously complicated circuit, and they are good enough actually to provide on the back a load of test diagrams of what you should be reading on the various test points. Having had a look at the board, there don't appear to be any test points that you can easily access, but nevertheless it does show how the circuit works. So by doing a little bit of reverse engineering on this, I think I can figure out where the likely culprits are going to be. This is the control board itself, and I'm not going to poke it too much because it is currently switched on, and I do have a bit of a reputation for electrocuting myself. But basically we've got the same circuit 6 times over, and 6 of these solid state relays which are driving the heaters. I've checked all the fuses and they're fine, and I've also swapped over these Schmitt triggers, which are just 4093 CMOS chips, and that seems to make no difference, so we know that these chips are working okay. The rest of the components are fairly straightforward. There's a couple of opto-isolators here which generally don't go wrong. There are a few capacitors, but they're not electrolytics, so whether or not these ceramics have gone I don't know, but the rest of it is just some diodes and resistors and a couple of transistors here and here. So there's not a great deal to it, and the fact that I've got the same circuit replicated 6 times means that if I just buzz around here with a multimeter, preferably when it's powered off, I should be able to check whether any of the diodes have gone, whether the transistors are okay, that sort of thing, and that'll give me a start, and I'll take it from there. Well, I've made an interesting discovery, and if I can get in here and actually measure it, I'm getting 0.98 across the base emitter junction of this transistor, and if I measure this one over here, I'm getting 0.68, which is about right, and over on this one I'm getting about, if I can get on the pins, there somewhere, here we go, 0.667. So that transistor there is reading far too high, and on this one here I'm getting an open circuit. And if I go base to collector, on that one I'm getting an open circuit, and on that one I'm getting 0 volts, which does not sound good, and on these two I'm getting 0.683, which sounds about right, and on this one I'm getting 0.663, which sounds about right. So these two transistors here and here are very definitely dead. So I'm going to have to take this board out and replace those. Doesn't explain why this heater is playing up, because these transistors measure okay, but these two, which control the first zone, they definitely appear to be dead. So I don't know why they've gone. I have a suspicion, having looked at the circuit diagram, but yeah, that definitely looks like a starting point. I can't find any other faults on it. All the diodes seem to buzz out correctly, but that's not right. So we'll start with those two and see if we make any progress. It's possible that there's some sort of cascade failure going on because they share this CMOS Schmitt trigger. So it could be that if these are actually pulling a voltage down somewhere, it may be affecting this chip, which would explain why this side is not working either. But I'll take those out and see how we progress. Okay, here we go. Keep your eye on those numbers and let's see what happens. I'll test zone 1 first. This is the one where I've replaced the two transistors. And is it going to trip out? No, not yet. Anyway, I can hear something clicking, so that heater band is warming up. See if the temperature goes up. It should, because if the heater band is okay, and I did measure the resistances and they all check out. Nothing yet on the there we go, 14. Right, well, it hasn't faulted out, so that's good. 15, and it seems to be warming up, so that's even better. 16. Well, I think we fixed it. Cool. Excellent. Okay, let's turn that off and have a go on the next zone. I'll turn that one off for sake of argument. Now then, let's see if those transistors have also fixed zone 2. 13 degrees, 77%, 89%, and it faults out. Right, okay, so there's a second fault, which makes sense because zone 1 went quite some time ago and zone 2 has been working fine. So it looks like there is an issue unrelated to the transistors. Okay, more diagnosis, and it means I'm going to have to take that board out again. Never mind, progress. Well, I've rechecked this zone 2 area and I haven't found any problems with the transistors, but what I have noticed is if I probe this Zener diode over here, which is in forward mode, I'm getting 0.691 diode drop across it, which is about right for a 6.8 volt Zener diode. They're heavily doped, so the forward voltage is quite a bit higher than you would expect for a normal silicon diode. And here I'm getting 0.77. This is on the area I suspect that is dodgy, and then on this one on zone 1, which we know now works, 0.69. So they're all consistent. But if I measure the reverse voltage, which I can't do very well because they're all in circuit, but on that one which we know works, I'm getting 0.965, and on zone 3, which I'm assuming works, I'm getting 0.975. But on the one where I've got problems, zone 2, I'm only reading 0.875, so that's quite a lot down. And due to the way that this is actually testing that forward voltage, it could well be that this capacitor, which is in parallel with the Zener, is leaking and would be pulling the voltage down. And if that were the case, then on our circuit diagram we should be getting 6.8 volts as a reference for our base drive on our transistor. If that's being pulled down, then this transistor isn't necessarily going to function properly. So that is a very suspicious capacitor there, I think. It's only a ceramic and they don't normally leak like electrolytics do, but I have had them go bad in the past. And you've got to bear in mind this is a fairly high temperature moulding machine, and although this isn't anywhere near the hot parts, there's quite a bit of heat coming out of the machine all the same. So it could just be a 30-year-old capacitor that's starting to leak and pull this voltage down. So I'm going to swap that out and see if it makes any difference, and if it doesn't, then it's probably the Zener, but there's not really anything else in that area that could be causing it. So the fact that there is a discrepancy there is a good lead, and well, we'll swap the capacitor and see if I'm right. Here we go again with a new capacitor. I did check the voltages actually after I swapped that out, and it has made a difference. That Zener that was reading pretty low is now reading the same as the others. In fact, the others have all increased in voltage as well. So something wrong with that capacitor, I'm pretty sure. Let's try zone 1 again, which has now had a chance to cool down. And that seems to be holding up to 100% and no fault on zone 1. That's good news. Give that a second. There we go, starting to go up and back down. There we go. No, it's holding, it's not gone. So okay, let's turn that one off, and oops, next one down, zone 2. Right, here we go. Will it trip? Yes, it will. So there's still a fault there. Damn, maybe it is the Zener that's dodgy then. Okay, we'll swap the Zener diode out. Right, I've now swapped out that Zener. I swapped the capacitor, and I've also gone and swapped both of those transistors just in case it was the same problem on zone 2. So we're currently 1920 degrees. Let's see what happens. Well, looks like we have a result. It hasn't tripped out. So I think it was the same fault. I think it was the transistors on both of them. And having had a look at the circuit, I can see there is a slight flaw in their design. In fact, I think there's an error in the manual as well. So whether that's come through from the design stage or just an error when they were compiling the manual, but either way, I can see why those transistors would be dying. So let's just turn all 4 zones on and see if anything goes wrong. But so far so good. And we're at 100% across the board. So it works. We fixed it eventually. I don't think that Zener and the capacitor were actually the problem, but we swapped them out anyway. I think it was all down to the transistors, and if I build a spice model of the circuit, I think I can explain exactly why those transistors are dying. I've drawn up the control circuit in LT Spice, and according to the manual this should be the input signal coming from the coupled inductor on the solid state relay. So this is essentially a 50 Hz main signal, and when it goes high it induces a 5 volt spike, and when it goes low it induces a -2.5, -3 volt spike. And I've simulated that using a couple of voltage sources, one to generate the high 5 volt spike and one to generate the low spike, and it's not exactly the same as what they show in their service guide, but it's a close enough approximation. That is coupled in through the inductor and goes into the emitter of this transistor. Over here we've just got the base referencing dividers. They're using some oddball resistor values, 1.21k here, and again over here 33.2, 4.99. I suspect these values were what they had in the pick and place machine and they're just reusing them. This is simply giving some current through our Zener to give us that 6.8 volt. There's a smoothing capacitor here, which I don't think is particularly important, but we swap them out anyway. And then there's a voltage divider to stick about 9.9 volts on the base. Our output is then coming from the collector, So this is essentially running as a common base amplifier. Our input is on the emitter, our output is on the collector. The base is simply doing whatever it does, and that again is fairly consistent with what they show in the manual, a 12-volt spike and dropping to almost -2, and it's all on a 12-volt supply obviously. So that's pretty good. That's a fairly close match to what they're showing. The Schmitt trigger is then simply tidying that up to give us a nominal 12-volt output. It's an inverting Schmitt, and that drops down to almost ground every time we get that upward spike, which again is pretty consistent with what they're showing. And then they're doing something a bit clever here. They're charging a capacitor through this resistor like that, which is what they show in the service guide, and then every time this Schmitt goes low, that capacitor can discharge through a much smaller resistor value back down into the Schmitt, so it's sinking current into this. I think they're being a little bit naughty here, to be honest, because if you look at the amount of current they're dumping into the Schmitt trigger, it's about 8 milliamps, and that's quite high. These things aren't quite rated for handling that much current going into them, so I think they should have made these resistor values maybe 10 times higher and made this capacitor about 10 times lower, but it seems to work, so I'll let them off with that. This is the second stage Schmitt, which is taking the capacitor profile and then simply tidying that up. Where's the signal? There we go. And that again is consistent with what they're showing. The duty cycle is a little bit broader than what they show in the manual, but there might be some artistic license going on here. And then that is simply feeding through a transistor and our opto coupler to give us our ultimate signal, which goes back to the main control system, and that's as shown here. Now, having looked at this circuit, I can see a few issues. For a start, this here is going low to about -2 volts, so that means we're pulling the input to this Schmitt down below ground, and although this is probably diode clamped, they're sort of relying on that to avoid damaging this thing. So they're bullying this poor Schmitt quite a lot, to be honest. They're dumping far more current in than I would have advised, and they should probably have put a diode clamp on the outside here just to get rid of that at -2 volts going in. But anyway, it works. The other issue I found in the manual is if we go right the way back to this diagram here, which shows the measured base emitter voltage of that first transistor, well, actually it doesn't. If we measure the base voltage, that's fairly consistent with the voltages we've got here, about 0.8 volts and about -1.5, and that's exactly what we're seeing here. But you'll notice that these spikes are on the 20 millisecond mark, whereas they're showing it on the -10. If we actually measure the base emitter voltage like that, and then get rid of this trace so we can see what's going on, this is on the 10 millisecond mark, but it's going down to -4 volts, not the -1.5 that they seem to be indicating here. And this leads me to believe that the reason these transistors were blowing is because if we get a voltage spike, the induced voltage is going to increase. So although they're suggesting a 5 volt positive spike, if that was actually a bit higher, say 8 volts, and we rerun the simulation, you can see that this now goes down to -7, and that means we're putting 7 volts across this emitter to base junction, and transistors generally only have a breakdown voltage of emitter to base of about 5 or 6 volts. For the BC546 family, it's about 6 volts. So that could well be the reason why these transistors were blowing. All you've got to do is have a main spike, slightly more voltage coming in, and that's going to go bang, and once that's gone down, it could be doing anything further down the field, and could explain why this transistor's gone as well. They could have solved that quite easily by simply sticking another diode in here. If they put a Zener diode in series with this network, that's then going to clamp the emitter to about 6 volts, and if they'd actually used a slightly lower value, this only has a 6.2 available, but you can see that clamps it even lower, and it doesn't affect the output at all. We're still getting the same output signal. So I think they should have put a 4.7 volt Zener in here just to protect that emitter base junction and prevent the transistor going pop, but because their service manual doesn't show that effect, maybe that's why it slipped through the net. The other thing is, if you do have that Zener in there, it takes the edge off these negative spikes that are going into the Schmitt. So they could have solved 2 problems with one simply by adding another diode there. And At some point I might add one to the circuit board if I get this problem occurring again. Obviously it's happened twice on 2 of the zones, but then I've had the machine for over a decade, so at the rate of once every 5 years maybe I'll just suffer having to change the transistors. But anyway, that's what I think has gone wrong. The machine is back online, that's the main thing, but it's interesting that the lack of one little component can cause so much troubleshooting.